Okay. Yeah, thank you for nice introduction and thank you for inviting me to the talk. Um, yeah, I'm Yugo Onishi from the Info Group at the MIT. Today I'm going to talk about my latest work about the quantum weight. And it is in this archive, so if you are interested in, please look at that. Okay, so let me start with some introduction. So in quantum matter theory, as you saw, we are interested in electronic properties of the solids, and probably the most classical theory of the electronic solid will be based on bond dispersion. So, for example, like you can imagine something like Boltzmann equation to describe the conductivity and stuff. But as you know, recent study shows that the not only the bond dispersion, but also the quantum states of electrons, represented by this Bloch wave function, are also pretty important to understand many other interesting features of solids, and which results in developing this topology or quantum geometry, this new concept in quantum matter theory. And one prominent example is the those topology and quantum Hall effect. So beginning with this integer or fractional quantum Hall effect in two-dimensional electron gas, um, this topological concept in quantum matter theory is developed, and now we all know that this integer or fractional quantum Hall effect can even occur without any external magnetic field. For example, in 2013, there's a report that the quantum anomalous Hall effect, meaning that the quantum Hall effect without any external magnetic field, is observed in experiments. And also, quite recently, last year, the Charles group at University of Washington reported that the fractional quantum Hall effect without any external magnetic field, and all these are can be described by so-called topological bound theory or like topological concepts. And basically, the most important result is that the whole conductivity is quantized to topological invariant called the Chan number. So these are basically about topology, but so now we are trying to go beyond the topology. So basically, the topology is something like counting a number of holes in a sense of this usual geometry, and because it is kind of discrete, you cannot have like 1.5 holes or something. So like it's kind of discrete, and also as long as it's kind of robust to a small population, you can not continuously changing. So it allows us to predict some properties of materials in quite robust way. And the one remarkable result is those quantum Hall effect. But at the same time, this only looking at this topology can miss many other interesting features. And so now what we are interested in is that the like more like a geometry, not only like topology. So for example, something like a length or area or curvature of this geometrical object. And these are basically, in contrast to this number of holes, basically continuous. Content can be continuously changing, and we can get more information than just looking at the topological information. And there are a lot of study that showing that we can actually observe the consequence of this non-trivial quantum geometry in various ways. One of the examples is nonlinear Hall effect, which can be described by very curvature or very curvature dipole, or so-called quantum metric, which I will introduce later. And so usually the Hall effect can occur only in a time-reversal symmetric system, but if you go beyond the linear response, basically it's a second order response, as long as you have this non-trivial geometric structure, then you can, in principle, have a Hall effect at second order as a second order response, even in the presence of time reversal symmetry. Another example might be a photovoltaic effect. For example, there is a photovoltaic effect called a shift current, and which is basically when you shining light when you are exciting an electron, and which gives rise to gives you some the change of the quantum geometry, and you can observe the change of the quantum geometry as the DC current. So basically, it's a kind of photocurrent effect, but it can be described as quantum geometry. And another interesting example is found in theoretical work by this Thomas group, and they also discussed the how this quantum geometry can appear in interacting systems, and they show that even in the flat band, where you usually do not have any, for example, group velocity, so like you may naively not expect any drastic transport phenomena. But once you start to take into account this quantum geometric effect, you can have drastic this transport phenomena superfluidity. So like these are all related to quantum geometry. So now the other like fundamental research, one important question is like how we can more directly probe this geometry, and how we can compare, for example, theoretical prediction or theoretical calculation with experimental results. So at least as for topology, we know that there are remarkable agreements between theory and experiment. As I always said, the Hall conductance, quantum Hall conductance, is nothing but this topological invariant channel number, and because of the topological nature, it's quite robust, and also theoretically, it can be exact even in strongly interacting systems, and of course, it is directly measurable in experiments, so like you can easily compare experimental results and theoretical results. Also, another important thing is this channel number is basically ground state properties. So you do not need to. So if you want to calculate theoretically, you do not need to go into look into the excitation or or non-equilibrium properties to get the channel number. So in topology, we have a very nice like we can observe experimentally, and we can relatively easily calculate these quantities, and it's easy to compare these results. But on the other hand, in quantum geometry, there's a lot of things going on, and for example, Riemann curvature, quantum metric, and their dipole and shift vector, and all this stuff are supposed to describe this quantum geometry. But of course, there is some phenomena that reflect these quantum geometric phenomena. But at the same time, if you want to compare these experimental results with theoretical calculation, there often have some there is often some kind of problems if you want to like literally compare directly the experimental results and theoretical results, because like those transport phenomena, such as for example nonlinear Hall effect, can involve scattering time or so some extrinsic factor can matter in experiment, in contrast to those quantum Hall conductance measurement. So the question is, if we want to literally plot the quantum geometry in real material, real systems, experimentally, and compare to theoretical results, we need to find something hopefully robust against the details of the system, and also hopefully exact and theoretically, and measurable in experiments. And another requirement that is preferable is the ground state properties. Again, like you do not probably want to look into very like high excited states. So this is the question what I want to ask. And the answer that we were proposing is the concept, new concept that we are proposing, the quantum wave. Okay, so this is the introduction, and I outline as the following. So I first quickly introduce the quantum geometry and like especially this quantum Berry curvature and quantum metric, and how they are defined and what the physical meaning is the what I'm going to describe. And then I will define the quantum weight, and after that I will see how this quantum weight can be show up as optical response and also structural factor. Okay, so let me first define what the quantum geometric tensor is. I will often just denote it as a QGT in the following slides. Okay, so the quantum geometric tensor, or basically quantum geometry, is basically describes the k dependence of the Bloch state or Bloch wave function, and it can be defined as like this. So here the u is the Bloch wave function of your band of your interest, and basically you are taking the derivative of this Bloch wave function and then take the inner product. But you want to have this some factor 1 minus p given by this projection operator onto your band, so that this entire quantity becomes gauge invariant. And if you look at this quantity, its real part, or like symmetric part with respect to the direction, like in k-space, is called a quantum metric, and the imaginary part is called the Berry curvature. And this Berry curvature is probably familiar to you, but actually the quantum weight is what they defined with this quantum metric. So let me explain more how this quantity is related to physical things. I want to give you some intuition. Okay. So the I think the intuitive interpretation of the quantum geometric tensor in k-space can be given by considering a two-band model, like the simplest systems you can get, where you can get a non-trivial quantum geometry. So, for example, if you think some in a cell with two sublattices A and B, and then basically the system should be described by two-band systems, two-band and two-band structure, and this band structure basically gives you a map from k-space to each Bloch wave function for each band. And because this is to a system, you can think of a kind of like a pseudo spin, and the Bloch wave function can be represented by a point on a Bloch sphere. And for example, North Pole represents a satellite A, and the South Pole represents satellite B, something like that. And if you go around in k-space like some path, then it will draw some line on Bloch sphere, and its area is represented by this Berry curvature, and the length of this path is represented by a quantum metric. So quantum metric is like they measure like how the Bloch states changed on the Bloch sphere, like how much they displaced on the Bloch sphere. Okay, now let me define the quantum weight. So it's closely related to Chern number, but basically the Chern. So let me first here I show you the definition of Chern number. So the Chern number is defined through the integral of Berry curvature, and the quantum weight is actually defined as pretty much the same, but instead of using the Berry curvature, what was we are going to use a quantum metric. So it's a kind of matrix. So we have basically in mind two-dimensional systems to make a contrast with this Chern number. But so in that case, this is 2x2 matrix. And there's a severe difference between the quantum weight and Chern number. So for example, or Berry curvature. For example, Berry curvature or Chern number can be either positive or negative. So for example, if you look at the Berry curvature, in some point in k-space, it can be positive, other point it can be negative, and it can, for example, all cancel out after you integrate, so that Chern number equals 0. So like Chern number sometimes cannot pick up the non-trivial quantum geometric information. It just cannot see any details. And also, like, depending on the, the symmetry, this Chern number can be zero. For example, if you have a terminal symmetry, Chern number equals zero, or like Bragg curvature can be completely zero over all the Briand zone if you have both an image and the terminal symmetry. But in contrast to this Bragg curvature Chern number, quantum weight or quantum metric is basically always non-negative. And so as long as you're looking at truly trivial, uh, like kind of plane wave like Bohr states, then basically you have some finite value for quantum metric or quantum weight. And also, another thing is that this quantum metric or like quantum weight would kind of witness this Bragg curvature or Chern number. Here, I mean by witness that once you have Bragg curvature or the Chern number, basically you should have the finite quantum weight or quantum metric. And actually, you can show there's some inequality between quantum metric and Bragg curvature, and hence the quantum weight and Chern number. And my thing is that this is absolutely variable Bragg curvature. So, like for example, even if you have Bragg curvature, no net Bragg curvature, as long as you have locally Bragg curvature, you basically have a finite quantum metric. So in that sense, like quantum metric is more sensitive to quantum geometry, local quantum geometric structure in case space than the Bragg curvature or channel. And also, I want to give you some interpretation about the intuitive interpretation about this quantum metric or quantum weight. And so one naive interpretation is to think of this quantum weight as some kind of spread of the wave function or like fluctuation of positional localization. So mathematically speaking, you can easily naively you can easily understand that this should be the case, because if you look at the expression of the quantum metric, it's actually look like a position fluctuation, because if you interpret the k derivative as a position operator. And you can show this more rigorously. And first, this kind of discussion is given in terms of the spread of a one-year function, and discussed in this literature by Malta and Vanderbilt. I think he was in the audience. But yeah. Okay, so let me think. Let us think a several example to get some grasp of how this quantum weight works. And again, like let me start with very trivial example in some sense. So, for example, if you think about something really classical, meaning that you do not have any spread of the wave function, or like you can also say kind of classical limit. In that case, basically, by classical limit, I mean that your wave function is basically almost like a delta function, so there's no spread at all. And in this case, again, like if you do not have any spread of the wave function, the basic quantum weight is just zero. So in this sense, like this kind of wave function is, or like this kind of insulator is kind of quantum geometrically trivial. But for example, once you include a quantum effect, it needs to be spread to some extent. And for example, you can consider like some kind of area of the harmonic oscillator. In that case, so once you include a quantum effect, you will have some finite spread. And in that case, you will have some finite delta x, and with that you will have a quantum weight proportional to this delta x square, or like its ratio to the unit cell area. So, and again, like if you go back to the classical limit, like take h about to zero, then again the quantum weight will be just zero. So in this sense, this quantum weight is kind of measuring some kind of quantumness of insulators. So the classical insulator should be just a point charge, but once you have quantum effect, you have this kind of spread which can be measured by quantum mechanics. Okay, let's move on to another a little bit more non-trivial example when this is a London level. So as you know, London level is very kind of topological systems, and in that case, basically because you have this cyclotron motion, cyclotron orbit, you have some spread of this wave function, at least of the order of the magnetic length. And it turns out if you calculate if you do math, then you can show that the quantum weight is actually equal to the Chern number in this case for any field actually. And this gives you some kind of intuition, like the quantum weight need to be just say equal or larger than Chern number. And actually, you can show it more rigorously again, as I already mentioned. The quantum weight is so once you have Chern number, finite Chern number, the quantum weight need to be finite, larger than the absolute value of Chern number. And then this can be again in real space, this can be understood with probably the analogy of this one level. And and another intuition, it may be found in a K-space. Again, like if you think of in terms of Bloch sphere, the quantum metric is measuring the length of the curve, but and the big curvature measuring the area, right? So so once you have like finite area, you need to, your contour that enclosing that finite area need to be finite, right? So like which basically means that once you have big curvature, then you basically need to have a quantum metric. And or like so you have a Chern number, then you need to have a quantum weight. So this might give you some intuitive understanding. Okay, another example is some Dirac. Another example we can think of is a massive Dirac phenomenon. So you can think of this kind of Hamiltonian, and there's this Dirac point with some finite mass, and then you can think of some topological phase transition like gap closing and stuff, and you can discuss how this across this topological phase transition, how this quantum weight will behave, and actually if you like calculate it, what you will find is that the this k quantum weight in the 2-dimension or 1-dimension actually diverges as the gap closing. So in that sense, at least lower than 2-dimension or 1-dimension, this quantum weight also can kind of probe this gap closing or topological phase transition. So with this, I hopefully I wanted to basically convince you that the quantum weight is important quantity, and so here's the brief summary. So basically, the quantum weight is defined by the quantum metric, integral of the quantum metric, and it is geometric quantity related to those big curvature, Chern number, and in contrast to Chern number, it's basically always non-zero, or like it can be non-zero under any symmetry, even if you have time reversal symmetry or time reversal symmetry and a emergent symmetry and stuff. And also, it's basically small in kind of trivial insulators. So if you have, so here atomic insulator, I mean that, but mean by that the something like a very like a small small spread of wave function compared to the insol. And so in that case, the quantum weight is basically very small. But so which means that basically in the boring case, like atomic insulators, yeah, quantum weight is basically small. On the other hand, if you have something interesting, for example, very curvature or Chern number, then quantum weight will pick up that information, and the quantum weight will be finite or like maybe you can say large. And also another feature is that it can diverge near gap closing. So where those quantum geometry can just like changes. And also, I basically in this talk, I just gives you non-interacting formalism, but you can generalize these concepts to interacting system, especially if it is interacting insulators, and we can do rigorously show these things. Right. This is the quantum weight, and what I want to now tell you is that okay, how we can measure this quantum weight, and there's a two-way to do that, and our paper is actually about the latter one, but I also want to mention about the first one, because it's also very promising way to practically implement in experiments. Okay, so basically there are two ways. Well, one is this optical response, and the other is a static structure factor. And experimentally, probably maybe optical response might be easier to do that. Or also static structure factor can be also in principle measurable in experiment by X-ray scattering. And for series, maybe static structure factor might be better because in in contrast to optical response, static structure factor is basically ground state properties. Okay, so let me explain the first optical response. And actually, the optical response is closely related to this quantum geometry. I mean, like one example is again like quantum Hall conductance, as you all know. But it is DC response and relates this whole conductivity to the Chan number, the ground state properties. But actually, you can relate optical response to both this quantum weight and Chan number by using some kind of sum rule. And maybe the more simpler or like even simple one is this the one about the Chan number. So basically, for example, if you think about this kind of integral, like imaginary part of sigma xy divided by omega, then and integrate over frequency, then actually this is nothing but the Kramers-Kronig equation. So like you can relate the imaginary part of sigma xy to real part of sigma xy, and in this case it is related to the DC real part of sigma xy, which is nothing but the Chan number. So if you if you divide by omega the imaginary part of sigma xy and integrate over frequency, then you will get some Chan number. And actually, the similar formula, similar sum rule integral gives you the other part of the quantum geometry, which is quantum weight, and which is first found by this Souza, Wilkins, and Martin. I think Mr. Souza is in the audience, but anyway, and then this is called SWM sum rule, and yeah, it's I think one of the first results that how we can experimentally measure the other half of the quantum geometry, the quantum metric or quantum weight. And also you can write them together like this. And actually this numerator is nothing but the describing the absorption of the circularly polarized light. So if you if this is plus, it is one of the hundredness of the circular polarized light, and if you put the sign, then it will correspond to the other hundredness of the circular polarized light. But anyway, so then this is nothing but the integral of the quantum geometric tensor, and giving you the quantum weight and Chan number as a real part and imaginary part respectively. And yeah, actually, if you use this, there is you can derive some interesting result about the gap, but it is another matter. If you look interested in, please look at this paper. Okay, and okay, next way to probe the quantum weight, which is most main results in our paper on the archive. So actually, you can relate this quantum weight to the static structure factor. The static structure factor is defined by this equation. So the log Q is the density operator with vector Q, and so basically it measures some sort of the density fluctuation, or you can also say that the equal time density correction function. And actually, what we found is that the static structure factor if you expand in Q, then this static structure factor is first in insulating case, this static structure factor starts at the second order, like quadratic term in Q. And what we found is that the coefficient of this quadratic term is nothing but this quantum weight or integral of the quantum metric. And the nice thing about this is that the competitive optical response, which is basically given by described by all this excitation and using a sum rule, this static structure factor is purely ground state properties. So once you know what the ground state is, then you can easily calculate without knowing any other like excitations. And also, static structure factor can be in principle measurable by X-ray sketching, and so it's also closely related to what we can measure, like practically in experiments. And also, again, I didn't give you much detail, but this expression itself is basically exact and holds in interacting systems, even in an interacting system in 2D. Once you generalize those quantum metric and those quantum metric or quantum joint tensor in appropriate way, as long as it is insulators. All right. So let me revisit again, like what in terms of the static structure factor, you can also think of kind of another intuition about the quantum weight. So because the static structure factor is something like this, you can actually convince yourself that this Q squared term is nothing but the representing kind of polarization fluctuation. And so, for example, like because the low Q, the density is given by the divergence of the polarization. So if you square this low Q, which is the SQ, then this should represent some kind of a p, something like a p square. The Q square quotient should be p square. So which is consistent with what we already talked about. Quantum weight is basically the polarization fluctuation or this position fluctuation. But this polarization fluctuation is most the general way to say this. Even you can say this in interacting systems. Also, let me briefly remark the relation between these two ways to measure this quantum weight. So basically, you can write the expression by the optical response as showing like this. Here, the chi is the polarization response, which is related to the conductivity by a factor of I omega. So if you look at this expression, then the left-hand side is basically representing the dissipation related to this polarization response. And right-hand side is, as I already noted, the polarization fluctuation. So in this sense, this might be more a kind of look natural because this dissipation and fluctuation both are about the polarization should be related through the dissipation fluctuation theorem. And actually, if you want to mathematically prove that, what you need to do is using this dissipation fluctuation theorem. All right, so this might be helpful to convince yourself that this optical response or like structure factor should be related to each other, and that they both can be the quantum weight. Okay, as a last part, I want to give you some example. Actually, this is calculated by Barun, my collaborator Barun in Northeastern University. He calculated this optical response in this manganese bismuth telluride. This manganese bismuth telluride is known as the intrinsic magnetic topological insulator, which can have a Chern number, and And it is experiment is observed that the anomalous Hall effect with quantum anomalous Hall effect. And he calculated the like optical responses, and by integrating that, you can also get the this quantum wave. And actually, this manganese crystallizes like layered material. So by changing the number of layer, you can change the Chan number and stuff. And here's the result for one layer, and the lower local panel is result for a 3 layer, and one layer have a Chan number 0, and the other has Chan number -1. And this is the real part of sigma xx divided by omega. So if you integrate this, then you will get the quantum weight. And the integrated one is this blue curve as a function of cutoff frequency. And the right-hand side shows the emergent part of sigma xy divided by omega, which after integration, usually gives you the Chan number. And first, maybe we should look at the Chan number part. So if you look at the emergent part of sigma xy divided by omega, and then it can basically take a both side, negative or positive, and basically fluctuate a lot. But if you integrate, then it's so in the case of one layer, it's basically always around the 0. And on the other hand, if you for Chan number 1 case, okay, again it's kind of fluctuates a lot, but it's soon after around I don't know 0.2 or something, then it will soon saturate to C Chan number C. On the other hand, if you look at the quantum metric part, this is always positive, and it's the integral it just keep basically increasing, and after like 6 eV, it's almost saturating. And one nice thing is that the okay, so the upper panel shows the topological trivial, and the other part is topological non-trivial. And you can see that the large contribution from long frequency in the case of the Chan number, finite Chan number in contrast to this case, and which represents the which means that you have a quantum geometrically non-trivial structure around low frequency, and which is captured by this quantum metric or quantum weight. Okay, so I'll stop here. This is summary and outro. So what we introduced today is this quantum weight defined as the integral of the quantum metric, and physically it represents the position fluctuation, or you can also think of the spread of the wave function, and that represents kind of like quantumness of the insulators. And the important, nice thing about this quantity is that it is accessible by both experiments and calculation. In experiment, you can measure it by either optical response or X-ray scattering, and in terms of calculation, once you know the ground state, you in principle can calculate through the static structure factor. And also another thing is that I didn't highlight that much in this talk, but basically this formalism can be extended to interacting systems. So if you have very strong interacting systems, for example, fractional quantum Hall effect, fractional quantum Hall systems, or multi-insulating systems, even in such a case, you can apply our concept and see how the system have a non-trivial quantum geometry. So with this observation, we believe that this quantum weight will be a fundamental material parameter of the general insulators strongly interacting and non-interacting, all encompassing strongly interacting, non-interacting systems, and it allows you to develop both experiment and theory and an understanding of the real materials. For future outlook, we would like to think about the relation of this quantum weight or quantum metric to other responses. So, for example, we know that at least for in the case of the quantum Hall effect, the quantum weight is kind of lower bounded by Chern number or quantum hole conductance in some sense. But the one question is whether we can get that kind of bound on the quantum weight. Like once you have non-trivial nonlinear response or like summer response, is there any signature in this quantum weight? And also here in this talk in this quantum weight is basically defined only for insulating systems, and so especially for a not an interacting system. So of course there are a lot of interesting material which is not insulating. So like similar concepts that you can experiment the probe and like also easily calculate by theory in stronger interacting metals or like superconductors. It will be very important, I think. Yeah. So that's all. Thank you for your attention, and happy to take questions. Thank you so much.
I have a question.
Yeah, sure.
Can you hear me?
Yeah, I can hear you. Yeah.
Yeah, thanks. Good talk. I have a question that you can find the Chern number just by doing just by looking at the Hall conductivity, right?
Yeah.
And let's say the simple case like integer quantum Hall system. Can you find the quantum weight by such quantity, not by thermal Hall conductance, but by some other quantity?
So, for example, for example, you can think of the following situation. So, okay, let's say you do not have any Chern number in your system. For example, let's say you have a temporal symmetry, and but still you can have the in case this, so you can have a local Berry curvature. So, for example, like in Brion zone, on right half you have positive Berry curvature, left half you have negative Berry curvature, and they are in net they are canceling out in total. And that kind of case is actually produce you, for example, kind of non-Hall effect, right? Like some interesting effect actually. But anyway, and so you can think of such a non-trivial quantum geometric system, but without any Chern number. And in that case, how you can probe this quantum geometric structure is, at least you cannot do that by just looking at the quantum Hall conductance, because it's just Chern number equals 0. But our quantum weight can probe it, because the quantum metric is bounded by quantum metric is bounded by the absolute value of the Berry curvature. So even if the right half and left half of the Brion zone have the opposite sign of Berry curvature, the G is everywhere like finite, right? It's always positive. So the such kind of non-trivial quantum geometric signature should be captured by looking at the quantum weight, quantum metric. Yeah.
I have another question.
Yeah, sure.
That let's say in an integer quantum Hall system, you can distinguish between different Chern number by looking at the Hall conductance, right? Or you can do it via short noise also.
So, sorry.
I'm saying you can distinguish between the two systems with different Chern number via short noise measurements also, right? Okay. So now can we do the same thing with the different material with different quantum weights?
So you're saying that you're saying that the by looking at only the quantum weight, how much we can distinguish, for example, topological phase or something. Is that what
yes, that's
yeah. So so if you say that the whether you can distinguish topological phase by this quantum weight or not, it's not, I think, there's no one-to-one correspondence. If you want to really distinguish the topological phase, then probably you should look at the the Hall conductance or other topological invariants. But what we are trying to do is not only the topological properties, we want to go more. We want to get more kind of more than something more than topology. So like again, like that's the example that I just gave, like half positive Berry curvature, half negative Berry curvature, and that kind of stuff. It is topologically the same phase as, for example, just the atomic insulators, where there's no Berry curvature at all in the anywhere in the radium zone, right? And so so what we are trying to do is more like rather than distinguish different topological phase, what we want to do is like even within the topological phase, what can how we can distinguish, and of course, like it can capture something about the topology, and at least like once you have topological non-trivial stuff in your system, then it will reflect, the quantum will reflect some of them, but like yeah, it's not like we are not like trying to distinguish the topological phase. Like we are trying to um get more than topological information. uh yeah, does that answering your
that's
question?
okay. That's okay.
Yeah.
That's okay. Yeah, I got my answer.
Mhm. Yeah. I think
Hi, thank you for the talk.
yeah,
I
thank
have
you.
a similar question.
Mm.
So this quantity is not quantized, right?
Yeah.
But do you expect that it would show any features if you have a certain symmetry, for example? Or like how do you like what information do we get from different numbers, if any number can be like
Hey, so again, it's kind of like like it's more like more than like more like a necessary condition to get something interesting. So for example, if you have like quantum weight, very small quantum weight, then it's very less likely. It's very almost not likely at all to get something interesting in your system, at least quantum geometrically, because the small quantum weight. I mean by small that the quantum weight is much smaller than one or something, almost zero. Then in that case, like basically you have no quantum metric, no Berry curvature, and it's almost pretty much like just atomic insulators. So it will so such a system, if you measure the quantum weight, or like if you calculate the quantum weight and you get a pretty small value, then which means that you do not have any hope that you can get anything interesting out of that system.
But it's not like if I have a certain symmetry, I would expect certain features or
Yes, but I mean, again, like if you have certain symmetry, okay. So what's often the case is that okay. So for example, if you want to find some I don't know, like for example, non-universals, then it often have some symmetry constraint, right? Like some material need to break some static symmetry or something, and but what often the case is that okay, even if the system breaks a certain symmetry, such a kind of effect can be pretty small, right? And so like what often happens is that you need to have large, for example, quantum metric large Berry curvature, or large, yeah, something large quantum geometric structure. And so if you want to, find, for example, some material with large effect, large quantum geometric effect, then you want something quantitative that you can measure, that you can use as a measure to okay, make a guess how large the effect can be. And at least this quantum weight can be kind of upper bound of your of the effect in your system. Like quantum weight is, if the quantum weight is too small, you cannot get like any.
okay.
That's it. Yeah, but yeah, that's what that's my point of view. And again, like so right now the quantum weight is the direct relation we found between the quantum weight and some other response is that one is by Sosa's and people found that those optical response and relation to the optical response, and the other is the static structure factor. And yeah, we need to have to explore more how much we can extract this quantum weight, how much information we can extract from the quantum weight, or like how it is related to other response. But yeah, my expectation is that once you have something non-trivial in your systems, then you need to have large quantum weight. That's my expectation at least.
Thank you. Yeah. I have another question. First of all, thanks for the talk. I really appreciated the perspective.
Thank you.
I have one question, which is probably a bit more historical. So say absorption of light seems like a topic that people have been studying for a long time.
Yeah.
Do you know if there are precursor works that are somehow identifying a related quantity, or was it just overlooked for the longest time? Do you know?
You mean historically? So, for example, this one.
So the left-hand side seems to be like something people could have done before, probably without division by omega. But so this was just overlooked for a while. Is that correct?
I think so. I mean, like, yeah. I should ask Ifo like in the audience, but like at least like at least I believe that this equality, like some role, is pretty important. But at least I don't see, like, for example, any like concrete calculation or like any like experimental analysis that actually using this some role. At least I don't know. Maybe I'm just not aware of, but yeah. So yeah, I feel like it's just kind of overlooked.
Mm-hmm.
Yeah.
I also have another question related to this slide. So is it a correct way to think about these expressions, or is it a correct perspective that integrating over omega ensures that you capture all of the occupied and unoccupied bands, and through that capture all the entire Brillouin zone? The denominator is required to ensure that the frequency dependent terms cancel. Is that a reasonable way to think about it? So to make quantity energy dependent.
Yeah. So like So one thing that I can say is that if you look into, for example, like expression, like detailed expression in, for example, Kubo formula or something, then what you need to divide it by omega is like, just as you said, like you want to cancel all the like energy term or like excitation energy appearing in the Kubo formula. That's a mathematical reason why you want to divide by omega. Other way to look at this is that so because we want to extract something about the block states, right? Like not the dispersion information, and so what we want to do is like something we want to extract something like transition probability, like and actually this conductivity or this part of like real part of, or like much part of this conductivity is represents the energy absorption, which means that it is kind of like a absorbed energy times the probability that it happens. And we want to extract only the probability part. Like we do not want the energy part, because it's not about the information. It's not information about the Bloch states. So, and by dividing by omega, you can cancel that energy part, so that it's more, in some sense, energy independent. And and to get the this quantum geometric quantities. Is that answering your question?
That's pretty much the answer I hoped for.
Yeah.
And one final question. So these identities in principle would also hold for 3D. There's nothing 2D specific here.
Yeah. So why I made a caveat about the 2D in for example in static structure factor is that the okay, so if you consider non-interacting systems or interacting system but with no long range interaction, only short range interaction, then everything just falls through. But in the 3D with long range interaction, there's a subtlety when you connect optical conductivity and the structure factor, which makes the connection to the quantum weight and the structure factor a little bit subtle, and that's what we like quite recently understand it, and actually we need to revise the archive preprint. So yeah, but that's why. So basically, if you start consider long range interaction in 3D, it can get more subtle. Yeah, so especially the relation to the static structure factor, and the optical conductivity is a little bit subtle. Yeah, so for this thing itself, it holds for even 3D or like with long range interaction. But the part that we need to be careful about is the part that we are relating the quantum weight to structure factor, and that part can be a little bit subtle if you consider 3D long range interaction. So that's why, yeah, I a little bit
I make comment on that subtlety.
Yeah.
The problem has to do with the polarization field. That means when you have a polarization fluctuation in 3D, you have to decide on the boundary condition. The way how the metric is computed, you have that with periodic boundary condition always. That means with zero field. So you keep the field to zero. That means you do that in transverse way. Instead, the structure factor is a fluctuation in the charge, so it is a longitudinal quantity.
Yeah.
Is measured. The fluctuation is done in a different way. In 2 dimensions, you don't have a depolarization field. That means if you have a polarization in the plane, there is no depolarization field in the plane, and that's the reason why in 2 dimensions you don't have problems. You can relate directly the structure factor to the metric, and you cannot do the same in 3D. You have to be very careful how the structure factor is ideally defined and measured.
Yeah, exactly. Yeah, thank you so much for that. And yeah, we had a discussion with Mr. Resta and Sosa and yeah, people, and yeah, so that's how we get to understanding. But yeah, anyway, so yeah, that's exactly because of the reason that just Raphael described. In 3D. Yeah, long range interaction may make a problem a little bit complicated or subtle, like because of the long range nature of the interaction, and it gives you crucial difference between longitudinal electric field, meaning that the electric field is aligning with the wave vector, and the transverse electric field, meaning that the wave vector Q is perpendicular to the electric field direction. These two population to the system will gives you essentially like qualitatively different results only in 3D long range interaction, and
I agree.
That will make a little bit more subtle. Yeah. Yeah, thank you so much for the comment.
Thanks a lot for the talk again.
Yeah.
Yeah, thank you.
Okay, yeah, thank you so much.